Okay, so in this video, I want to continue our discussion of z-scores. Very important. We talked about some of the conceptual stuff and looked at a generic normal curve where we didn't really have the numbers on the x-axis. But now I want to talk about maybe some more practical and realistic examples. And we're going to learn or keep using the unit normal table. People need to be comfortable using that because it's very powerful. And the unit normal table is predicated on a normal distribution of data. And in fact, if you are, do the homework problems in the chapters, oftentimes they'll start a problem by saying, assume that these data are distributed normally. Normal curves are ubiquitous, so that is, generally a good assumption. If we have reason to question that assumption, then we have to be careful about using the unit normal table. Later on, we will be sort of assuring normality by doing something called the central limit theorem, but I don't want to get too far ahead. So let's use sort of a more realistic example here, a less conceptual example. Of course, we're still going to use the concepts that we've learned. Let's look at the distribution of IQ scores, okay? So IQ stands for intelligence quotient, and hopefully you learned something about IQ when you took Intro to Psych, if you're a psych major. And it's a quotient, and it refers to someone's mental age divided by their chronological age. And this is a very common multiple choice question in an intro psych exam. And of course, the two options that are given is the correct option. But oftentimes you'll see IQ. One of the options that's incorrect is chronological age over mental age. Once again, I'm going to try to help you here, give you some advice. If you memorize this and you forget on the exam, then you're kind of out of luck. But if you understand that higher IQ means you're smarter, lower IQ means you're not as smart, that is, as an intelligence test, then you can actually figure out the difference between this correct answer and the incorrect answer. Because all we need to do is put in some hypothetical data. If someone has a mental age of 10, but their chronological age is 14, that's going to give you a lower IQ score, right? Than if someone so it's mental age over chronological age. If their chronological age is 14 and they have a mental age of 10, that would give you a large IQ. But you would know that if someone has a mental age of 10, chronological age of 14, that means they have a low IQ. So this is the correct ratio, okay? The correct quotient. However, if someone had a mental age of, let's say, 16, but they were only 12 years old, that would be a much higher IQ, okay? And so it's mental age over chronological age. It's another one of these things that you could actually figure out instead of memorizing. Anyway, here's what happens if your mental age, let's say you're 12 years old, and, your mental age is 12, and you're 12 years old, then that gives a ratio of 1 that's multiplied by 100. I don't know why that is, but then that would give you an IQ of 100. If your mental age was 14 and your chronological age was 10, this would be greater than 1. We could figure this out. Let's see. 14 divided by 12 is 1.17. Multiply that by 100. So this person would have an IQ of 117. If they had a mental age of 8, and they were 12 years old, then that would give us 8 divided by 12. That would give us an IQ of 67, okay? 0.67 times 100. So that's how it works. I don't really need to get into that right now for this stats class, but all that being said, what we find is the average IQ score is 100. That is, mental age equals your chronological age. So that would give you an IQ of 100. And we typically don't know a whole lot about population parameters, actually. The mean is 100. By definition, that's the average. But so many millions of IQ tests have been given, we sort of know what the standard deviation is, and that is the standard deviation is 15. Okay? That's generally considered, those are the population parameters for IQ scores. All right, well, big deal. All right? Well, here's what we can do. Knowing the parameters, knowing how z-scores work, using our unit normal table, we can start to answer some interesting questions here about what this curve looks like and the percentages or proportions underneath this curve. For example, let me ask this question. What would be the proportion or the percentage of people that have an IQ score that's greater than 120? Okay, greater than 120. Someone who has an IQ score of 120 is above average. Okay, if they were 10 years old, they would have a mental age of a 12-year-old. All right, and we could do the other ages as well. But that's a pretty impressive IQ score, I think. Let's take a look. I'm going to put that score here. I'm going to put that score on the graph. Remember, these are all x values here. These are all x values. And what I'm saying is, what percentage of the population has an IQ above 120, right? So what we're talking about is this area in the curve. And what we can do now, when we're talking about areas under the curve, is we can use the unit normal table to get that information. So if I can convert this x value into a z-score, then I go into my unit normal table and I can actually see what percentage is in that tail. Okay, so let's do that. Here's my z-score formula, right? Here's my z-score formula. And so I have my x value is 120, right? My mean is 100. So I'm comparing how far away is 120 from 100. And then I'm going to put that in terms of, or in the currency of z-score, standard deviation. So I'm going to divide by 15. My z-score here then is 20 over 15, which is 1.33, and that's positive, okay? Positive 1.33. Well, guess what that does for me? It allows me now to go to the unit normal table and find out what percentage of people are in the tail, okay? And so let me just erase this. I'm going to pick up my textbook. You need your textbook again, okay? If you don't have it, pause the video and go get it because you'll need it. And I'm going to look at Appendix B, the unit normal table, and I'm looking for a z-score now of 1.33, okay? And so just look at it in numerical order here. Z-score of 1.33. And in the tail, so this is column C in our textbook, in the tail it tells me there's 9.18% of the people who score above a 120, okay? And if we want to, we can talk about percentiles. For percentiles, I'm looking at what's the percentage of people here and below, and that means the body. And it's just 100% minus the tail. But I can also read it from the book, 90.82. Okay, so there's 90.82% in the body, and that's what I would call the 90th percentile. So having an IQ of 120 is pretty far out, man. Pretty far out there. There's only a little bit more than 9% of the people that score above 120. And you're in a 90.82th percentile. Okay? So that's pretty far out there. And we know this because we have the unit normal table. By the way, the unit normal table was generated using calculus, right? We're looking at area underneath the curve in a certain range or at a certain point and beyond. And so somebody who knows calculus is able to get that area. Sometimes when people take calculus, they don't understand what it's used for. This is a perfect example of what it's used for. Okay. Let's do another example using IQ because it's I kind of consider it a nice clean example. People are familiar at least with the terminology IQ. It measures intelligence, and so let's do another one. And I'm going to have you see if you can do it on your own. So I will pause momentarily, and if you want to stop the video, you can. See if you can do this on your own, like I'll be asking you on an exam. And then, of course, I'll do it as well and show you. So here are the parameters. We have the mean is 100. Standard deviation is 15. Let me ask you this question. What percentage of the population would we expect to see have an IQ score below 95, let's say, okay? So what we're going to do here is we're going to say, okay, here's our x equals 95, okay? And what percentage of the population scores below 95? So I shade in this area. When you're doing these questions, you absolutely need to draw the curve and shade in the area that you're looking for. I would have a difficult time answering these types of questions if I didn't sort of sketch out the curve and identify what I'm looking for. It's very confusing, okay? Sometimes when people come to my office and they ask me, I really don't understand how to do this, and I see them doing all sorts of math, and they've never drawn the curve. I'm like, I mean, you don't have to draw the curve, but man, it makes it a lot easier if you do, because you can sort of identify what you're looking for. And of course, for area underneath the curve, for percentages, for proportions, the questions will be asked in different ways. That's life, okay? But what we're going to do is we're going to rely on that very powerful tool, the unit normal table, okay? So what we have to do here is figure out what z-score this corresponds to, and I'm just going to put my values in here, 95 minus 100 divided by 15. So my z-score is a negative 0.33. Okay, a negative 0.33. So once again, let me reach down and get my textbook here. And I'm going to look up I'm going to look up that proportion now in the tail, because that's what I've shaded in here. 0.33 in the tail, 37.07%. Okay, which makes sense compared to what we did before, because this is only 5 points away from the mean. When we were at the 120, we were 20 points away from the mean. So the tail here is going to be larger. Just double check. 37.07. Okay. So that's the percentage of people in the general population who have an IQ below 95. Now, I want to talk about the 3 P's here, because percentage can be expressed in proportion, right? That's what's in the table. So this is out of 1. This is out of 100. We've talked about this before. But I can also talk about this, and this is going to become very important for us. I can also talk about this in terms of probabilities. If we know that 37.07% of the population has an IQ below 95, then I can say, you know what, if I randomly chose someone from the general population, the probability that they would have an IQ below 95 is 37.07%. Okay? Now, randomly choosing someone from the population is much more difficult than most people realize. I mean, how would you randomly choose someone? You can't like go to the mall and randomly choose someone, because that doesn't include people with it's not likely to include people with very, very low IQs. Okay? I wouldn't just walk down the street and point at someone and say, okay, you're a random person in the population. That's not really what random means. It means everybody in the population has the same chance of getting chosen. All right? I get a little bit, one of my pet peeves is when people use the term random when it's nothing close to random. Like some people are like, oh, I just randomly, chose a song off my playlist. I'm like, nah, not really. Maybe there's an algorithm within your program that can do that, but you didn't do it. Or somebody says, well, I just went to a random store in the mall. And I'm like, no, not really. Random is a much more technical term when we talk about statistics and science and so on and so forth. Anyway, if we were able to randomly choose somebody from the general population, I would expect a 37% chance, 37.07, that they would have an IQ below 95. Okay. Notice, by the way, we have a negative z-score. I'm using the unit normal table. We can disregard the negative just because it's a symmetrical curve. And so whether it's a positive 0.33 or a negative 0.33, the tail is still 37.07%. Okay? And I could do this, with all sorts of examples. Okay, I could do this with all sorts of examples. Okay, let's see. Let me do another example. We'll get out of IQ. I'll bring IQ back in a minute for a more complex or more challenging question. Let me do this example. Let's suppose that I have been really pushing the college to give more money to students who have really performed well in their classes, and so maybe we can give an extra $1,000 to all the students who are really performing well as a reinforcement, as a reward for students that do good schoolwork. And so let's do this. Let's assume, I don't know why it went up so high in here. And it doesn't really matter, does it? But that's just who I am. Let's assume that GPA we'll use GPA as our measure of academic performance, even though I would certainly rather use overall z-scores. But let's suppose we use GPAs for our measure of academic performance. And let's suppose that, let's do this, and I don't know what this would be. Let's suppose that the average for the school is 3.15, okay, GPA. Of course, not everybody scores 3.15. We know that, and so we have to acknowledge that there's some variability. And so and I'm just making this up again, let's say that the variability for GPAs is 0.40. Okay? And I want to give, let's do this, I want to give that $1,000 scholarship to anybody that's in the top quarter of the class, top 25%. Okay? The question then is, what GPA do you have to get this extra $1,000? Okay? So that's the information. What you should do as your first step here is to say, all right, well, top 25%, where are they? Top 25% is right there, perhaps. Okay. That means 25% in the tail. If I have that information, I can use the unit normal table as well. Of course, the unit normal table is, they don't give percentages, they give proportions. So the first thing I need to do is convert this to a proportion so that I can then use the table, okay? So, and I'm looking for an X value, that is, I'm looking for a GPA. But I'm going to convert this to 0.2500, okay? Proportion, percentage. It's really the same numeral, it's just where you place the decimal, okay? So I know that that's the proportion in the tail. So now I'm going to use the unit normal table in a little bit different way. I'm going to look at column C, and I'm going to look for 0.2500, 0.2500, 0.2500. Well, I have 0.2514. And I have 0.2483, but I don't have 0.2500. Now the question is, do I use the closest one? Well, if I was a real stickler, and I wanted exactly 25%, because if this was a university that had 30,000 students, that might make a difference having a little bit more than 25%, right? If I was a stickler, what could I do here? What is a tool that you have in your statistical toolbox? Yeah, I could. I mean, let me go back. Here's a z-score. Here's the proportion. Z-score here is 0.67. Z-score here is 0.68. I could actually, if I wanted to, if I was a stickler for that exact 25%, guess what I could do here? Yeah, you guessed it. We could do interpolation. We could do interpolation if we wanted to get that exact number, somewhere between 0.67 and 0.68. I'm going to assume right now that you could do that interpolation if forced to do it, okay? But we don't want to get too bogged down in that, so let's just use something close, okay? I'm giving us a little bit of a break here, okay? Let's just use the closest one. And so we know that the z-score here is 0.67, okay? So as long as I have As long as I have 3 out of 4 of these, I can solve for the remaining variable, right? So 0.67 is my z-score here. I know that from using the table. 0.67 gives me a tail of 25%. Actually 25.14, but we won't tell anybody, okay? 0.67 is the z-score. I'm looking for the x value. I have the mean, 3.14. The standard deviation is 0.40. Okay? So let's solve for x in this case. This is high school algebra. Okay? If you need help, please contact me. I can help you with that. All right? My assumption is the fact that you're in college, you can do high school algebra. That has to be an assumption. When you learn something, we expect that it sticks for a while. So let's do this. 0.67 times 0.4. Okay. So that is 0.268 is equal to x minus 3.15. So I'm going to add 3.15 to each side. So my answer is 3.42. Okay? 3.42 is the GPA that you need to get this extra $1,000 if we're going to give it to the top 25% of the students. Okay? That is the GPA that you need based on these population parameters. Okay? And that would put you at the 75th percentile. That would put you at the 75th percentile, right? 25 this way, 75 down this way. All right. Let's keep these parameters up here. And let me do another example here. Let's see if you can do this. Suppose that we decide that people are in the bottom 10% of performance, that we're going to dismiss them for a semester. Yikes, okay? So what I'm talking about here is bottom 10% as a proportion. That would look like this. And so what x value, that is, what GPA would you have to be dismissed from the school if these are the population parameters, okay? So I'm going to go to the unit normal table again. I'm going to look for 10%, 10%, 10%. Well, I can get 10.003. That's going to be close enough for us. The z-score is minus 1.20. Okay? Once again, I will solve for x in this case. Make sure now you pay attention to the negative, okay? So 1.2 times 0.4 equals, so it's negative 0.48, okay? And I'm going to, let's see, 3.15 minus 0.48 equals 2.67, okay? 2.67 here would be my x value. That's where you would be dismissed from the school, okay? Now, that seems a little harsh, right? Well, it's probably because this is not realistic. This would probably be a little bit larger. It doesn't matter, folks. I'm just showing you how this stuff works in terms of using the z-score, identifying places in the curve. I mean, these folks are in the 10th percentile. If these were the parameters, that's pretty low. Okay, so that's how it would work. Okay. All right. So I'm going to go back to my IQ example, and because I have another type of question that I'm going to ask you. Remember, the mean is 100, standard deviation is 15. Okay, those are the population parameters. And let's do this. Let's suppose that we want to talk about maybe gifted students, okay? Now, that's a hypothetical construct that needs to be defined, right? We need to have an operational definition for that, for this. And so let me suggest, and by the way, I don't know if this is true. I should have Googled it before the lecture, but it just doesn't matter. Throwing these numbers in, because you're going to have questions that you won't know anything about, but given these parameters, you'll be able to figure out, what's going on. That is with z-scores and proportions. Let's suppose that gifted means that you have a score, an IQ between 110 and 120. Okay, and that's not a minus, but it's between 110 and 120. Okay. And the question here is, what percentage of the population would get that moniker, would get that designation of being gifted? Well, let's see what it looks like on the graph. I'm still going to go to the graph. I'm going to say, okay, here's my x of 110. Here is my x of 120. So this is the proportion of the curve. This is the percentage of the blocks that I'm asking about. Okay? Now, we're going to rely on the unit normal table. So let's quick do the z-score for 110, the z-score for 120. Of course, we did the z-score for 120. That's 1.33. And I would hope, if I said, does that make sense to you, that the z-score is 1.33, I would hope that you would say yes. Now, sometimes people are resistant to this. Well, I plugged it into the calculator and this is what I got. Well, we have to remember what z-score means. It tells us how many standard deviations away from the mean we are. Well, 120 is 20 points away from the mean. My standard deviation is 15. If I'm 20 points away from the mean, that means I'm one standard deviation plus a third of a standard deviation. So it's 1.33. That should make sense to you once you think about it, okay? Don't get lost in the math now all of a sudden. People don't want this to be a math course, and then all they want to do is math, because that's tends to be the easy part, because the concepts are more difficult. What about a score of 110? How many standard deviations away from the mean is that? Well, it's 10 points away from the mean, so that's 2/3 of 15. Okay, so this is 0.67. Okay, make sure you round appropriately, folks. If you have 0.666666, that should be rounded. If you're using two decimal places, that should be rounded to 0.67. Okay, 0.666666 is rounded to 0.67. We're not just chopping off the rest, we're rounding. So we're good to go for our unit normal table because we have the z-scores. There's a problem here, though, a little bit, because I'm not really looking for a body or a tail. In this example, I'm looking for a slice, right? And the unit normal table doesn't have slices. So what should you do? Well, the first thing you should do is just panic. Oh my God, oh my God. No, don't panic. Listen, I'm going to give you a very valuable piece of advice here. If this was made out of construction paper, and I asked you to cut out that portion of the graph, would you be able to do it, that slice? And of course you would say, Dr. Speck, that's ridiculous. Of course I could do it, right? I take my scissors, I would cut here, and I would cut here, and then I would give you that slice, okay? By the way, just as a little side note, if we made this curve precisely out of construction paper, very carefully, and I did cut this slice out like that, and I weighed it, the weight of that slice would actually tell me what proportion of the entire curve. I take the weight of the slice, I put it over the weight of the entire curve, it would actually show me the proportion. It really works like that. Anyway, if I gave you a pair of scissors, would you be able to cut out that slice? The answer is of course, of course. Okay, so what would you do first? Well, I would cut here. Okay, why are you cutting there? Well, some people would say, I'm cutting there to get rid of all of this. Okay? And I'm like, all right, well, let me ask you this. What is this? Well, this is the body for a z-score of 0.67, right? I mean, that's what you're doing. So let's look up z-score for 0.67, the body for a z-score of 0.67. I'm right here at this line. This is the tail. This is the body, okay? The body for a z-score of 0.67 is 74.86%. So that's what you're cutting off. Let's start with the entire curve. Let's start with the entire curve. We're going to cut off that portion, okay? Then what would you do with your scissors? Well, you would take them and you would cut right here, right? I mean, that's what you're going to do. What are you doing in that case? Well, you're getting rid of this piece. Well, what is this piece? Okay, this piece is the tail for 1.33. And so what is the tail for 1.33? We've done this before, and that is 9.18. I cut off the tail at 1.33. I cut off the body at 0.67. What is my slice that's left over? 100 minus 74.86 minus 9.18. We're left with 15.96. Once again, figure outable. Okay? Now, that's not the only way that you can conceptualize your scissor cutting. And I'm telling you, man, trust me on this one, if you approach this as a scissor cutting person to get that slice, you will make your life easier. Okay? Somebody might have done the same first cut with their scissors. Got my pair of scissors, I'm cutting this way, okay? And I'm going to ask you, why did you cut there? To get this slice, why did you cut there? And the person says, well, I cut there because I know I'm going to have to get this entire tail. Okay, that's what I'm starting with. When you cut here, you're conceptualizing it as isolating this large tail. Okay, that's awesome. Now we have to ask ourselves, what was the tail for 0.67? I'm looking at my book here, looking at the book. 0.67, 0.67. The tail for 0.67 was 25.14. Okay, that's what I got here. And then what did you do? Then I took my scissors and I cut here. Well, what you're doing now is getting rid of this smaller tail, which was 9.18. And guess what the answer is? 15.96%. Same. It has to be the same. It has to be the same, folks, because it represents the same slice. Now, I don't care if you do it this way or if you do it this way. That either way is fine with me, okay? Because you're going to get the same answer, hopefully, if you keep your wits about you. By the way, there is a third conceptualization of this. By the way, for me, personally, I like the cutting off this and cutting off this. That is, I'm getting rid of what I don't want. What's left over is what I want. But it doesn't mean that's any more correct than if you did this minus this. The problem is people are just like doing lots of things and they don't know what they're doing. So keep your wits about you as much as you can. Ask me a question. There's a third way that we could do this, by the way. And what we could do is, if somebody could take their scissors. I'm still going back to the scissors. I'm not kidding about how this will help you conceptualize. And they could have cut here first and said, well, I'm doing that because I want to get this big portion here. Well, what is that big portion? That's actually the body for 1.33. Using my book. The body for 1.33 is 90.82. Okay. Then what I'm going to do is I'm going to subtract the body for 0.67, and we know that's 74.86. Guess what? When we subtract these two, same thing. It has to be. 3 different ways that you can, when you're cutting, you're conceptualizing that in your head. 3 different ways. Each way is valid. What I see when students have problems doing this, oftentimes what I see is they're trying to memorize. Okay, so it's tail, so it's body, tail, so it's No. Use your scissors, your mental scissors. You're cutting these pieces. You really, if you think about it very physically instead of the abstract math, then I have more confidence that you can stay with it and, get that correct answer. Okay? Either way, you're going to do fine. For me personally, I just think it's cleaner to say, okay, I want this slice. Let's get rid of this. Let's get rid of this. I start with the whole curve. I subtract each of the let's get rid ofs, and I go from there. Tail's fine. Body's fine. In this case, you have to be careful with those conceptualizations if you cross the middle, okay? Absolutely have to draw the curve. Absolutely, okay? All right, so I'm going to give you sort of a problem to set us up for the next video, a very similar problem, and see if you can't find the solution. Okay, so let me do this. Okay, let's assume that for a certain track event, a collegiate track event, NCAA, let's assume that the time it takes you to run this track event, and again, I'm kind of talking uninformed. Sometimes I look this stuff up on Google and use the actual data, but it really doesn't matter. I just want people to be able to manipulate these numbers in a normal curve. Let's assume that the running time for this particular track event is normally distributed across the country. Thousands and thousands of track and field students do this event, and let's say that the average for the event, the time it takes you to get around the track or whatever it is let's say 57.37 seconds. Okay? So a minute, what would that be, like a quarter mile? I don't know, or however many meters. It just doesn't matter that much. And the standard deviation, of course, because not everybody has the same running speed, right? The standard deviation is, let's say 6.11 seconds. Okay? So those are the population parameters for a normal distribution of running times for this particular event. All right. So let's do this. Let's say that the United States Olympic Committee has decided that the people who are the fastest, let's do this. If you're in the fastest 15% in the country, you're going to get a letter or email inviting you to come to the annual Olympic tryouts. Okay? If you're in the top 15%, come in, you're going to get an invitation to try out for Olympic tryouts. So the question is, what time do you need? What time do you need to get an invitation from the United States Olympic Committee? Okay, that is the question. We know the parameters. We know we want the fastest 15%. So what time do you have to run to get that letter? All these times are official, sanctioned. The school submits to the NCAA. The NCAA is going to look at this, and they're going to say, well, we're going to send the fastest 15%. They're going to get an invitation from the USOC. Okay. What's the first thing that you should do? Please draw the graph. Figure out where, the area under the curve. Use your z-score, use your normal table, and you'll be able to figure out what running time you need to get that invitation. And we'll start from there in the next video.